Bismillahirrahmanirrahim. I am Riaz Junejo and I am delivering the video lectures for the course of Applied Electricity and Electronics. The course code is CEE103. This course is being offered by the Department of Electrical and Computer Engineering, Kamsat University, Islamabad campus for the semester of fall 2020. This is a series of lectures and today we are going to discuss lecture number 14. Today's topic is nodal analysis without voltage sources. This is a series of lectures and in total we'll be discussing 32 lectures. And for the students information, these lecture slides and videos are being prepared from the textbook of Fundamentals of Electric Circuits. The author is Alexander Sadiko. So let's start. Today we are going to start new chapter, that is chapter number 3, methods of analysis. In this chapter we will be discussing two very important and powerful techniques, that is nodal analysis and mesh analysis. These are the general kinds of analysis methods. We can apply nodal analysis to any kind of circuit. Also mesh analysis is very general, but there's one limitation that we'll see that what is that limitation. But nodal analysis in particular is very important and useful analysis technique, such that we can apply this method to any of the given circuit. Previously we have seen that how we can simplify the series resistances or parallel resistances, or how we can simplify the resistances that contain delta or Y networks. But these methods that we discussed previously, these methods are not general. That is, we cannot apply to any general given circuit. But nodal analysis general method, we can apply this method to any of the given circuit. So obviously, I remember that in the end we will be want to develop some method that is in general, that is it is not particularly related to either series or parallel or Y delta transformation. So let's start. Section 3.1 Introduction. First important tool that we used for the solution of the circuit was Ohm's law, and then we discussed Kirchhoff's law. So Ohm's law and Kirchhoff's law provide a fundamental methods to understand and analyze the circuit. Obviously, Ohm's law and Kirchhoff voltage law and current law are very important and fundamental methods. But remember, these are not some kind of general methods. So we will develop two more powerful techniques here, that is nodal analysis based on Kirchhoff current law, and then we'll see or develop mesh analysis that is based on Kirchhoff voltage law. So these two important methods that we'll be discussing in this chapter, and these are based on Kirchhoff's law. So with these two methods, we can analyze any circuit by obtaining a set of simultaneous equations. One more important thing that we should remember, that previously when we were using Kirchhoff voltage law or current law, the number of equations were actually enormous. That is, one important point is that we must reduce the number of equations when simplifying the circuit. Obviously, if there are more equations to solve, then problem will become very complicated. So in this again some kind of objective is to reduce the number of equations. So we'll see that nodal analysis and mesh analysis will greatly reduce the number of equations that we can simultaneously solve. So first tool that we want to discuss is nodal analysis, and this is section number 3.2. So nodal analysis provides a general procedure for analyzing circuit using node voltages at the circuit variables. So in this technique, we will not be discussing or examining the individual voltages or currents in the branches or elements, but we will be discussing or analyzing the node voltages of the circuit. So obviously in this case we must find the number of nodes and we must define that what are the reference and non-reference nodes. So we know that in any circuit there are two types of nodes. One is first kind of node is known as reference nodes, also called ground, datum, earth, or chassis node. So remember that when we want to measure the potential across any element, so we must find the that voltage with respect to a given reference point or node. So that reference point or node is known as ground node. So other than that reference point, there will be non-reference nodes. So generally reference node is denoted in the circuit using this arrow as a symbol, or this three lines are using this. So these are the symbols in the circuit for reference node. So reference node is assumed to be at potential 0. So this is important, that reference node is assumed to be potential. It might be not at 0 potential, because we are going to measure other potential potentials with respect to that reference node. So we'll assume that reference node potential is 0. So there's only one reference node in any given circuit. So this is again a very important, that in any given circuit there will be only one reference or ground node. So next important nodes in the circuit that are present are actually non-reference nodes. So non-reference node, so potential of a non-reference node with respect ground node is generally non-zero. So obviously once we have selected the ground or reference node, then there will be other node that we can label them as a non-reference. So potential or voltage of the non-reference node with respect ground is generally non-zero. So that potential is known as actually node voltage. That is potential of a non-reference node with respect to reference node is known as node voltage. So there could be more than one non-reference node. So this is again important, that there is only one reference node, but there could be more than one non-reference node. So for nodal analysis, Kirchhoff current law is applied at a non-reference node. So this is important, that KCL is always applied at a non-reference node, because applying KCL at a reference node will not give any extra information. So KCL is always applied at a non-reference node. So avoid having too many equations. KCL should be applied to such a node where at least three branches are connected. So important is that since we have defined a node is a joining point in a circuit where at least two branches or elements are connected, but we can use KCL at a node where at least three branches are connected to have a different set of equations. This is very again important. So when applying Kirchhoff current law, remember that since we are going to apply Kirchhoff current law at a node, so we must see that what are the incoming currents at that particular node or non-reference node, and what are the outgoing currents. So we must sum the incoming currents, and then we must sum the outgoing currents. So according to Kirchhoff current law, that sum of the incoming currents should be equal to the sum of outgoing currents. So remember that to apply KCL, one important thing is that we must know the direction of each current in the branch that is connected to the given node. So current obviously flows from higher potential to a lower potential point in a resistance. So this is important, that if we want to apply KCL in a certain branch where a resistance involved, remember that current always flows from higher potential point to lower potential point. So we should be able to write the current equations in each element connected to non-reference node. This is very important, that if we want to apply Kirchhoff current law, we must be able to write the current equation for each element in a non-reference node, or we should have the value of the current in that branch. So current in each branch starts and ends at nodes, that is reference or non-reference node. This again obvious. So nodal analysis is best choice in circuits involving current sources only. Again, we can generalize that if we have a circuit if we have only current sources in the circuit, so which method should be particularly applicable there. So we can say that in that case nodal analysis is the best choice. To simplify the matters, we'll assume for time being that circuits do not contain voltage sources. First of all, we'll see the circuit that do not contain any voltage sources. Next we'll see that how we can analyze the circuits that contain the voltage sources. So let's list or enumerate the steps to determine the node voltages. So select a node as the reference node. Already mentioned that assign voltages V1, V2 up to Vn minus 1 to the remaining n minus 1 nodes. The voltages are referenced with respect to the reference node. So we can, if we have selected reference and non-reference node, then we can apply assign voltage symbols to non-reference node voltages, that is V1, V2 up to Vn minus 1. So assign the current direction in each branch using conventional current direction method. That is, in essence, we are going to apply Kirchhoff current law, so we must know the current direction in each branch. So if a branch contains a current source, take current direction in that branch same as that of the current source. So there could be some possibility that branch contains a current source. So since in current source we are already given the direction of the current, so we can take the current direction in that branch as the current direction of the current source. So if an element is in between non-reference node and ground node, current direction is from non-reference node to ground unless there is a current source present in that particular branch. So if let's suppose that we have a case that a particular branch is in between non-reference and reference node, so in that case we can take the direction from the non-reference to the reference node. So if an element is in between two non-reference nodes, then direction is arbitrary. So if let's suppose we have a situation, where element is in between two non-reference nodes, then current direction is generally arbitrary. So generally, for writing the equation, we can use Ohm's law. We know that according to Ohm's law, I is equal voltage divided by R. So generally, current in any element is V higher minus V lower divided by resistance. That is higher potential minus lower potential divided by resistance. Again, you can see that to write down the equation, we must know the resistance of that element. So apply KCL to each n minus 1 non-reference nodes using Ohm's law to express the branch currents in terms of node voltages. So we can easily apply that KCL to n minus 1 voltages, so we can then have n minus 1 equations and n minus 1 variables to, so finally we can solve. So solve the resulting simultaneous equations to obtain the unknown node voltages. So let's see the example that we and let's see that how we can use this theory that we have developed here. So calculate the node voltages in the circuit shown. This is a simple circuit. Here you can see that in this circuit there is a current source, 10 ampere direction is given, 5 ampere current direction is given, and there are three other elements that are resistance 2 ohm, 4 ohm and 6 ohm. So first step, let's draw the circuit by assigning the non-reference nodes current direction as shown in the diagram. So now we can redraw this circuit. To apply nodal analysis, remember that we must have the current direction in each branch. So in this branch you can see that we have the current direction from right to left, we have the current direction here, and we don't have the current direction in 6 ohm resistance. So we can assign this 6 ohm resistance direction by ourselves. That is, since 6 ohm resistance is connected in between node number 2 and ground node, so we can assign this direction from non-reference node to reference node. Similarly, you can see that 4 ohm resistance is connected in between node number 1 and 2, so we can assign direction from node number 1 to 2 or from 2 to 1, because we don't know that which potential is higher in this case. Similarly, we can assign the voltage current direction in 2 ohm resistance branch from node number 1 to ground. So one thing you can observe that there are two actually non-reference nodes. This is node number 1 and this is node number 2, and this is a ground node. So this means that there are total 3 nodes. One is ground node, a reference node, and 2 are non-reference nodes. So this means that there will be two unknown arising, that is voltage at this node and voltage at this node with respect to ground. So let's call this voltage as V1 and let's call this voltage as V2. So since there are two non-reference nodes, so we need two equations. Since obviously there will be two variables arising, so we must have two equations. So we can apply KCL at node 1 and we also can use Ohm's law. So at node 1 you can see that we have incoming current I1 is equal to 5 ampere, we have outgoing current for I2 and we have outgoing current I3. So according to KCL, sum of the incoming currents should be equal to the sum of the outgoing current. So we can say that I1 should be equal to I2 plus I3. So we have the value of I1, that is 5 ampere, and we can write the equation for I2 using Ohm's law. We know that current is voltage divided by resistance. So voltage across 4 ohm resistance, you can see that this 4 ohm resistance is connected in between node number 1 and 2, and current flows from this V1.2 or V1 node to V2 node. So we can write down the potential difference across 4 ohm resistance as V1 minus V2. So according to Ohm's law, current will be V1 minus V2 divided by 4. And here 2 ohm resistance, current in this 2 ohm resistance is I3. So this 2 ohm resistance is connected in between V1 and ground. Since voltage of the ground is 0, so we can say that current in this 2 ohm resistance will be according to Ohm's law V1 minus 0, that is higher potential minus lower potential divided by resistance. So V1 minus 0 divided by 2. So now we can easily simplify this equation as we can take LCM, we can collect the like terms and so on. You can extend these steps in between here. I skip those steps. So anyway, equation will be 3V1 minus V2 is equal 20. So let's call this equation number 1. You can see that this is not simple equation. This is actually this equation involves two variables. So to solve this equation we must have another equation. So we will be now constructing second equation, and we will be using Kirchhoff current law at node number 2. So for second equation, let's use KCL and Ohm's law at node number 2. At node number 2, you can see there are 4 branches connected to node number 2, that is 4 ohm, 6 ohm, 10 ohm and 5 ampere, 10 ampere and 5 ampere current sources. So you can see that I2 is actually incoming and 10 ampere current is actually incoming current. So some of these incoming currents should be equal to the outgoing current. You can see that this 5 ampere current is outgoing and 6 ohm current in 6 ohm resistance is also outgoing. So we can proceed. So I2 plus I4 should be equal to I1 plus I5. So for I2, you can see that I2 is actually current in 4 ohm resistance. Already we have the equation for I2. This is V1 minus V2 divided by 4. So here that equation substituted plus I4, and I4 is actually current this current source, that is 10 amperes. So V1 minus V2 divided by 4 plus 10, that should be equal to I1. I1 is 5 and then current in 6 ohm resistance, this will be V2 minus 0 divided by 6. So this will be the equation for the KCL at node number 2. Again, we can take the LCM, collect the like terms and so on. So we will get equation like minus 3V1 plus 5V2 is equal 60. Again, remember that here we have taken the LCM and combined the like terms. So now we have two simultaneous equations in two unknowns v1 and v2, so we can simultaneously solve equations 1 and 2. So we'll get v1 is 13.3 volts and v2 is equal 20 volts. So in this case we have now node voltages at node number 1 and node number 2. So now we can calculate the current, that is I1. I1 we have already 5 ampere and I2 is equal to actually V1 minus V2 divided by 4. This is minus 1.67 ampere, and I3 is actually, if we see the circuit, you can see that I3 is V1 divided by 2. So I3 will be equal to 6.67 ampere, we have to substitute the value of V1 here. Similarly, I4, we have the value of I4 at 10 ampere, and I5 is V2 minus 0 divided by 6. This is 3.33 ampere. So now you can see that value of I2 is actually negative. So it means that current direction that we assumed for I2 is actually wrong direction. But the current actually flows in the opposite direction, but numerical value is still same, that is 1.67. So in this circuit, we assume that current is actually flowing from point 1 to point 2, but actually current is flowing from point 2 to point 1, because obviously V2 is larger and V1 is smaller. So in this case, we know that current flows from higher potential to lower potential. So that's why actually I2 is negative. All other currents are actually positive. So this means that we have assumed the correct direction in the remaining current except I2. So I2 turns out to be negative. This shows that current flows in the direction opposite to the one assumed. So let's see another example. Determine the voltages at the nodes in this circuit. This is a simple circuit. In this circuit, still we have two current sources and three resistances. So again, you can see that this is a ground node, and except the ground node, there are two non-reference nodes. That is node number 1 and node number 2. Remember that this is same node as second node, and this is also same node as node number 1. So we have two non-reference nodes. This means that we will be needing two equations to solve solutions. So let's assume that voltage here with respect ground is V1, and voltage here with respect ground is V2. So let V1 and V2 be the node voltages at nodes 1 and 2. So next we'll be assigning the current direction in each branch. Here current direction in this branch is given. So this 4 ohm resistance is connected in between non-reference and reference node. So we can assume the direction from of the current from non-reference node to ground. This 5 ohm resistance is connected in between node number 1 and 2. So since these both are actually non-reference nodes, so we can assume current direction from node number 1 to 2 or from 2 to 1. So in this case, we have assumed from node number 2 to 1. Similarly, in 5 ohm resistance, current direction is not given, so we can assume current direction from non-reference node to reference node. So this is the direction here, current direction is given. So now we have the current direction in each branch, so we can apply Kirchhoff current law at each non-reference node to find the equations. So let's start applying Kirchhoff current law at node number 1. At node number 1, you can see that there are three branches connected: 14 ampere, 4 ohm, and 5 ohm resistance. So you can see there at node number 1, current from the 5 ohm resistance is incoming to the node. Current in the 4 ohm resistance is outgoing from the node, and this is also incoming to the node. So this means that there are two incoming currents. So this means that sum of the incoming currents should be equal to the sum of the outgoing currents. So current in this branch is 14 plus incoming current in 5 ohm resistance, because again we can use Ohm's law. So current is voltage divided by resistance. So this will be V2 minus V1 divided by 5. That is starting our initial potential point minus ending potential point divided by resistance. So V2 minus V1 divided by 5. That should be equal to the sum of the outgoing current, since there is only one outgoing current. So that is current at 4 ohm resistance. So current in 4 ohm resistance will be V1 minus 0 divided by 4, or V1 divided by 4. So we can easily take the LCM and simplify. So LCM will be 20. So we can multiply overall with 20. So this will be 280 plus 4v2 minus 4v1 is equal to 5v1, or 9v1 minus 4v2 is equal to 80. So this is the equation number 1. That is equation for the node number 1. Next we'll be actually using Kirchhoff current law at node number 2. Again you can see that at node number 2 there are three branches connected: 7 ampere, 5 ohm, and another 5 ohm resistance. And current in currents are actually outgoing. There is no incoming current, so we can say that sum of these incoming outgoing currents should be equal to 0. So let's apply Kirchhoff current law at node number 2. This is one current outgoing, so 7 plus outgoing current in 5 ohm resistance. This will be V2 minus 0 divided by 5 plus V2 minus V1 divided by 5. That should be equal to 0 there, because there is no actually outgoing current. So this means that we can now simplify. We can, LCM will be 5, so we can multiply with 5 overall. So this will be 35 plus V2 plus V2 minus V1 is equal to 0, or V1 minus V2 V2 is equal to 35. So let's call this equation as equation number 2. Now we can simplify or solve equation number 1 and 2 simultaneously. So we'll get V1 is equal to 30 volt and V2 is equal minus 2.5 volts. So now we have the node voltage at node number 1 and node number 2. So let's see another circuit. For the circuit shown, obtain V1 and V2. Again, in this circuit there are two non-reference nodes. So this is a non-reference node, this is a non-reference node, and this is a ground node. So this means that there will be two unknown voltages. There will be two equations arising, and you can see that in this circuit there is no voltage source involved, only current sources are involved, so we can easily use nodal analysis. So see the figure for the direction. So we have identified node voltage. Next will be assigning the current direction. So for current direction, you can see that 10 ohm resistance is connected in between node number 1 and ground. So we can assign the direction from node number 1 or non-reference node to reference node. Similarly, 5 ohm resistance is connected in between V1 and ground node. So direction of the current will be from V1 to ground. Similarly, current direction in 4 ohm resistance will be from V2 to ground, because this 4 ohm resistance is connected in non-reference and reference node. But this 2 ohm resistance is connected in between two non-reference nodes, that is V1 and V2. So current direction will be arbitrary here, that is it can be from V1 to V2 or from V2 to V1. And here in this branch 6 ampere current is flowing, direction is given, so no need to assign the direction here. There is no current direction already given, so we can apply Kirchhoff current law at node number 1. Before applying Kirchhoff current law at node number 1, we can see that there are 4 branches connected to node number 1: 2 ohm, 6 ampere current source, 5 ohm, and 10 ohm. So this means that there will be 6 current that we should consider. So out of those, in fact 4 currents. So out of those 4 currents, you can see that one, this is outgoing, this is outgoing, and this is outgoing, and this is outgoing. All these 4 currents are actually outgoing currents. So we can say that some of the outgoing currents should be equal to some of the incoming currents. So in this case, since there is no incoming current, so that sum should be equal to 0. So we have started from current in 10 ohm resistance. So 10 ohm resistance is connected in between one node V1 and ground. So in current will be according to Ohm's law, voltage divided by resistance. So voltage will be V1 minus 0 divided by 10. That is V1 divided by 10. Next we have actually 5 ohm resistance. This is connected in between V1 and ground node. So current will be V1 minus 0 divided by 5. That is V1 divided by 5. Similarly, current in 2 ohm resistance, you can see that this current starts from V1 and ends at V2. So current will be, our potential difference will be V1 minus V2, and current will be V1 minus V2 divided by 2. That is voltage divided by resistance. And current in this branch is 6 ampere. So plus 6 should be equal to 0. So now we can easily simplify. You can see that LCM is 10. So this will be V1 plus 2V1 plus 5V1 minus 5V2 plus 60 is equal to 0, or 8V1 minus 5V2 is equal to minus 60. This is, let's call this equation as equation number 1. Now we'll be applying Kirchhoff current law at node number 2. Again, you can see that at node number 2 there are 4 branches connected: 2 ohm, 6 ampere current source, 4 ohm, and 3 ampere current source. 6 current in 2 ohm is actually incoming to node 2. This is also incoming, this is outgoing, and this is incoming. So there are 3 incoming currents and 1 is outgoing current. So according to Kirchhoff current law, sum of the incoming currents should be equal to the sum of the outgoing current. So we can start from the current in 2 ohm resistance. Already we have the equation for the current in 2 ohm resistance. This is V1 minus V2 divided by 2 plus another incoming current is 6, another incoming current is 3, so plus 3, that should be equal to current in 4 ohm resistance. So since 4 ohm resistance is connected in between V2 and ground, so voltage across this resistance will be V2, current will be V2 divided by 4. So we can simplify, take the LCM. Actually LCM is 4, so we can multiply with 4. So this will be 2v1 minus 2v2 plus 3 plus 6 9, 9 into 4 36 is equal to v2, or 2v1 minus 3v2 is equal to minus 36. So now we have the equation 1 and 2 in two variables, so we can solve these equations simultaneously. So we get actually v1 is 0 and v2 is equal 12 volts. So so now using this technique we can simplify the this circuit. You can see that v1 is 0, so this means that there will be no current actually in 10 ohm and 5 ohm resistance. Thank you so much. Next we'll be seeing that how you can apply the nodal analysis to circuit that contain voltage sources as well.